Let's continue on from our previous test benches and talk a little bit about cocotb, HDL data types, and HDL handle values. So in short, handles are objects to allow for access to any signal name in our HDL design. In previous examples, we saw how to get and set values in a simulation via this .signalName.value notation. Accessing the value property of handle objects will return a binary value, which is a cocotb class. What this .count.value actually returns is a binary value class. So if we print that and run make to run our test bench, we can go up and see that it returned the class type, which is a binary value. So what can we do with binary values? Well, we can access their value as we've already seen, but we can also do other things, like access the bin string. If we run make again on that, we can go up and see that it printed out all x's. So we had a 4-bit value that was x on the first clock. This was the count from our previous example, so it was x on the first clock. If we run it for a couple more clocks, maybe 5, and we run make again, we can see that on each iteration of the clock, the count increases by 1 after 2 clocks because we held reset. And this is binary, so we go 1 and then 2. So that's one thing you can do with binary values. You can access various bits of the binary value. Another thing we can do with binary values is access the integer or signed integer value of the binary string of the underlying value. If we run make on that, our test bench fails because there's an unresolvable bit in the binary string x. So unfortunately, x in high Z states cannot be you cannot determine the signed or integer value from those states. So we'll have to fix the test bench a bit to make sure that we can print those out. We've run that again. We started outputting it after 2 clocks. So you'll see that you get the assigned integer out 1, and then we got 2. Let's run that a little more to make that example a little more clear. So let's run it for 10 clocks. 1, 2, 3, 4, 5, 6, 7. You can cook up your own binary values if you just import cocotb.binary and import the binary representation and the binary value. Then you can do things like set a variable to a binary value. We'll say the value is 10. It has 8 bits. It's big endian. And we'll call the binary representation 2's complement. Now if we print out bv.value, we should get 10 out. Since this is not a cocotb test, we can simply run it as a Python script. We get 10 out. Another cool thing you can do with binary values is set particular bits to particular states. So let's say I have a 8-bit signal, and I want the first bit to be x, the second bit to be z, the third bit to be z, either lowercase or uppercase z work, and same with x, lowercase or uppercase x work, and then the last 4 bits are just 0, 1, 0, 0. We'll call that 8 bits. We'll say it's big endian, and again, we'll set the binary representation to its complement. Now if we print that out and check if it's resolvable, and also we print out the bin string version of it, we should see that it is not resolvable because it has x states or z states in it, but we can print out the bin string contained within it, which is exactly what we set it to. As a final example, let's create a binary value that has 10 bits. Another way to do that is setting in bits directly. Say big Indian is false, and we'll say the binary representation is binary representation, once again 2's complement. We can set that value directly by accessing integer and giving it a negative 128 value. There's been discussion on cocotb boards that in future iterations of cocotb that binary value will be deprecated and replaced with bit, logic, and logic array. So let's go over those briefly so that you're ready for that change when it comes. We can play around with these by importing cocotb types and import bit, logic, and logic array. And then from cocotb.types.range, we can import range. So what can we do with logic values? Well, logic value is a single bit. We can simply declare a bit as x, and then we can print it out and get x out. We could also assign it to 1 and get 1 out. A logic array works a lot like a binary value that we just saw. You can create a logic array by calling the class and then setting individual bits to various states. Now if we print out A, the bin string of A, we get those bits out. With logic arrays, you can also define lists where you set each list member to a state representing a single bit. Now if we print out a.binstring, we should get those same bits out. Another thing you can do with logic arrays is define them a lot like you would directly in HDL. So you can define a series of bits and then give it a range and say 3 down to 0. Now if we print the bin string of A out, we should get those bits right back out. We can also define it the other way around. So let's create another variable and say this is 3 down to 2, 3 down to 0, and this is 0 to 3. And let's set these bits opposite. Now if we print out the first element of each array, we should get a 1. We should get a 1 and a 0. So that was a little bit about cocotb's handles, binary values, logic, and logic arrays. Hope that helps. Thanks for watching.